Suppose I have a mass on a spring. It's bobbing up and down. I'd like to know how to describe this. This is a very common kind of system in nature, from chemical bonds to quartz crystals to musical instruments to buildings and bridges, so we'd really like to understand it. The first thing we can do is attach a marker to the back of our mass as it bobs up and down. This way we can trace out its motion. Imagine the piece of frictionless paper is moving behind the mass as it bobs up and down. The motion is still one-dimensional, up and down only, but we're using the horizontal scale to represent time. In this case, our paper is moving about 3 centimeters per second, so 3 centimeters represents 1 second on this piece of paper. I notice that the mass is moving slowest when it's at the top and the bottom, it's changing direction, and it's moving fastest when it's in the middle, right there. I also notice, if I know a little bit about mathematical functions, that this looks sinusoidal to me. I'm not sure if it is, but I am fairly sure it's periodic. It looks like the period, or the distance from trough to trough, or crest to crest, is also 1 second. This is coincidental in this system, but other systems might have other periods. I'd like to have a way to predict what the period is, how quickly this mass will move up and down, if I know a few things about the system. In this video, we're going to see how to use a few simple physical laws and a little bit of mathematical knowledge to make those predictions. This mass on a spring system is one example of what we call a simple harmonic oscillator. This means an oscillating system whose period of motion doesn't depend on its amplitude, but we'll get into that more later. Let's look at how we can derive some mathematical descriptions for this system using some well-known physical laws. We'll start with Newton's second law. It's a very good place to start, usually in physics. Newton's second law says the acceleration of a body is directly proportional to the net force on the object and inversely proportional to its mass. This should be true for any massive object as long as we know what the net force is. Here F represents the net force. We don't want to forget that. This is the way I prefer to write the law, but frequently you'll hear it as F equals ma, and today that's going to be convenient, so we're going to use F equals ma. Let's take a look more closely at what that means. If F equals ma, well, what does a represent? We know that a is the time rate of change of velocity, or a is dv dt, so we can write this as F equals m dv dt, where this symbol just represents the acceleration a. We can also pull this derivative operator off of the v so that we can expose it more clearly as an operator acting on v, which is a function of time. I can only take a time derivative of something if the thing itself is a function of time. So we're making explicit that this is an operator acting on a function. We can do the same thing again, though, because v itself is just dx dt. So this right here is v. Notice now we have two generations of differentiation going on. We have d by dt of x. This leads us to other ways to write this. Here we're making explicit it's d by dt of x, which we can count as 2 d's and 2 dt's, which is why frequently we write second derivatives using Lagrange's notation, this notation with the d's, as d squared x dt squared. You might have been wondering, why isn't this called dx squared dt squared? Why is it d squared x dt squared? And this is why, because it's this operator acting twice, so we can see the operator itself is squared, being applied twice to the x. There are several ways to write this. This is Lagrange's notation. Sorry, I misspoke. This is Leibniz's notation. Leibniz was one of Newton's rivals. We also have Newton's own notation. He loved to write it this way. He uses one dot over the symbol for each derivative. You can see how there'd be advantages if you had a sixth derivative. This could be d6x dt squared, but Newton would have to write something like this, which gets to be a little bit unwieldy. This isn't the only notation. Something you've probably seen in math class is F equals mx prime prime, and this is the notation associated with Lagrange. So we have the notation of Leibniz, of Newton, and of Lagrange. You can see that by this time, calculus was becoming kind of an international affair. Newton was living in Great Britain, Leibniz in what is now Germany, but then was the Holy Roman Emperor, and Lagrange, as you might guess, in France. The second law we're going to move on to relates force to something other than acceleration. This is Hooke's law. No one knows what Robert Hooke looked like because we have no surviving paintings of him. This is a modern rendition of Hooke based on his descriptions of his appearance by a modern artist. Hooke's law relates the force on a mass to a spring applying the force to that mass. And it says that the force, F, is equal to a negative constant times x, where x represents the stretch from equilibrium of the mass. Let's take a look at what this means pictorially. Suppose I have a 1 Newton mass hanging from a spring. By 1 Newton, we mean that near the Earth's surface we have about 100 grams hanging. Remember that we take the mass in kilograms and multiply by 10 to get the weight in newtons. If I have a weight of 1 Newton, that means I have a tenth of a kilogram, or 100 grams. This mass is hanging in equilibrium. We're going to plot its stretch in meters versus the force it took to create that stretch. So here we have the mass hanging at rest, and it's 20 centimeters from the top of the spring to the bottom of the mass. It doesn't matter where we measure, the top or the bottom of the mass, as long as we're consistent as this stretches. Suppose we double the amount of weight hanging to 2 newtons, the spring will stretch further. We let it come to equilibrium so it isn't bobbing up and down, and we measure that it's 30 centimeters in length now. We repeat it again for 3 newtons, or 300 grams, and measure a length from top of the spring to bottom of the mass, 40 centimeters, and I think we can see the trend. A straight line. This is what Hooke's law says. It says that the force exerted by the spring is equal to a negative constant, which we'll call k, times the stretch of the spring. And you might be wondering, if I have a positive slope here, why am I seeing a minus k? That's because what I've plotted is the applied force represented by the amount of mass that I was hanging on the spring. But since the spring is in equilibrium, that's equal to minus the force exerted by the spring. So the force exerted by the spring equals equal but opposite to the force exerted on the spring. That's Newton's third law. Here I can see that the slope looks to be that I get, for an increased load of 1 Newton, I get an additional 10 centimeters of stretch. So the slope here is going to be 1 Newton per tenth of a meter, which is the same as 10 newtons per meter. So this spring constant, k, in the case we're looking at here, is 10 newtons per meter. If we had a larger spring constant, it would mean the spring was stiffer, which would mean I would need a bigger force to get the same amount of stretch on the spring. We have Newton's law, F equals ma, and Hooke's law, F equals minus kx. If ma equals F and minus kx equals F, then ma must also equal minus kx, so we can set these equal to each other. Now we know that a has some relationship to x. What is that relationship? Well, a is x prime prime. So mx prime prime equals minus kx. Or x prime prime by itself equals minus the ratio k over m times x. What does this equation mean? You might be used to looking at algebraic equations, which look like, say, 3x minus 2 equals 7. What's that going to be? Well, we know how to solve this. We can find a value for x that makes this equation true. X just represents a number in this case, and this is called an algebraic equation. But it's not the only kind of equation. This equation is something different. It's called a differential equation, and they are very useful in physics. A differential equation is just an equation that has derivatives in it. Here we have 2 derivatives, so this is called a second-order differential equation. And we aren't looking for a value for x. We're looking for a function called x. And the function called x is not x of x, it's x of t. This is a function of time. So we can make this more explicit. This is called explicit notation when we note that x is a function of t explicitly. X is some function of t, And you can read this in a sentence by saying, I'm thinking of a function. The function I'm thinking of has this property. The function's second derivative, or its curvature, is equal to a negative constant times the function itself. So the more positive this function becomes, we're saying the more negatively curved it is. So this will become more and more tightly curved as this gets a bigger and bigger positive value, and vice versa. As this function takes on more and more negative values, it will become more and more positively curved. An additional fact that must be true is if this function is equal to 0, then its curvature must also be 0. Its second derivative must be 0. So if we sketch this out, I know that when the function I'm thinking of is equal to 0, it isn't curved at all. If it's not curved at all, then it's going to get more positive as I move to the right. But as it gets more positive, it needs to become more curved and curved downward. If it's curved downward, it'll eventually get smaller. As it gets smaller, it becomes less curved, so that when it comes back to 0, it isn't curved at all. As it's negative, getting more and more negative, it's going to become more and more tightly curled as a smile. This means this can't go on forever. It has to get smaller and smaller in magnitude as it approaches 0 again, and it gets less and less curved. So, of course, this is the function we're going to get, because we've already seen the solution. We can have functions that look like that. We could have functions that look like this. So, you know, the usual suspects. We call these sinusoids. How can we actually find a solution to this equation, though? Well, one of the best ways to solve a differential equation is to already know the answer, and then guess and check. It's great to guess an answer you know is correct, and then demonstrate that it's true. Let's see how to do this in detail. So remember, we're looking for a function of time such that the second derivative of that function is equal to negative k over m, where k is the spring constant and m is the mass, times that function of time itself. We already know the answer because we've seen what it looks like. This function x of t, let's make this guess. Guess that x of t is equal to some constant a, representing the amplitude or how big that motion is up and down, times, let's say, the sine of, we'll use this curvy w, which is the Greek letter omega, omega t, plus some constant, phi. So I have these two constants, a, the amplitude, and phi, which is called the phase. And why do I need those? Well, I know from experience and from theoretical knowledge, which we'll gain over time, that if I have a second derivative in my differential equation, that represents an equation with two derivatives in it, and we know that to undo a derivative, we need one of these guys. So if I need to integrate, I know that when I integrate some function of x dx, I'm going to get some antiderivative. I'm undoing the derivative, and there's going to be one of these, plus a constant. So this means that if I have two integrals that I need to undo two derivatives, then I'm going to need two constants. They're called constants of integration, and what they represent in physics generally is initial conditions, such as how fast the mass is moving at t equals 0, and how far from equilibrium it is at t equals 0. We'll uncover some details about that over time. So if the function x of t is a sine omega t, what is x prime of t? Well, I know that the derivative, let's take a look at what sine looks like, just to remember. If sine looks like this, we can just kind of remind ourselves, what is the slope here? Well, it's about some positive number. And what is the slope right here? It's 0. The function is flat. So this is smoothly coming down to 0. What is the slope right here? Well, it's as negative as it ever gets. So it's smoothly coming down to some negative value. Here the slope is 0 again, though, so we're coming back up to 0. And this trend continues. Here we have a maximum value, the same maximum value, And I can tell this is our old friend cosine. So the derivative of sine is cosine, which you might already know. Derivative of sine is cosine, cosine of the same stuff. However, if we had a faster oscillation, if this omega was bigger, we'd have a bigger slope. How much bigger? Omega times bigger. This is called the chain rule, that we pop out an omega each time we take a derivative. So the derivative of sine is cosine times the derivative of what's inside. We're taking a derivative with respect to time, so this guy is linear in time. This is a constant, so the derivative here will be omega. So we get an omega out. So we have a omega cosine of omega t plus phi. Taking a second derivative, x prime prime of t, it's just the first derivative of the first derivative, and we're going to pop out another omega. I see that this function starts with zero slope, but then the slope becomes more negative, so I remember that this derivative of cosine is negative sine. A is still along for the ride. The arguments of the trig function are still omega t plus phi, and I still have omega out here, but I got a second omega from my second derivative, applying the chain rule again. But notice I have an A, I have a sine, and all of this is the same. So the only things that are different are that I have a negative sign and an omega squared that I didn't have for x of t. So x prime prime is minus omega squared x of t. Now let's compare. Does this satisfy what we're looking for? Which is up here. X prime prime of t is minus k over m times x of t. X prime prime of t is minus omega squared times x of t. So this is true if omega squared equals k over m. So we just found a way to tell what the frequency is. The frequency of this oscillator is going to be the square root of the spring constant divided by the mass. What's that mean? If I make the spring constant higher, if I make it a stiffer spring, then I'm going to have a faster oscillation. If I have a more massive mass on my spring, then I'm going to have a slower oscillation, because my denominator, when it gets big, makes the whole fraction get small. This is true in all kinds of oscillators. The stiffer I make something, if I tighten the string on my piano or my guitar, I'm going to get a higher frequency. If I make the strings more massive, like in the bass end of the piano, they're very thick strings, you can take a look under the lid, and they have lower frequencies of oscillation. So that is how we determine the frequency of the simple harmonic oscillator. What do these constants mean, A, omega, and phi? Well, let's take a look using Desmos.